We started talking about inverse functions yesterday, but I guess what we're more concerned with, I mean, inverse functions are still very important, don't get me wrong, but what we're really interested in is the inverse trig functions, because that's going to allow us to do some good stuff in the motion later on. So let's define our inverse trig functions. So the inverse sine of x, well, let's have a look at our sine of x so we can work out where to restrict our domain. So domain's all real x for the actual curve, and the range, of course, is in between -1 and 1, but it doesn't pass the horizontal line test. So we want to get a piece of the sine curve, which will cover the whole range if possible. And ideally, I mean, there's several different spots we could pick there. We'd like to include the origin, if we can. So the logical restriction is in between -pi on 2 and pi on 2. It'll get the origin and it'll cover the whole of the range. So the range doesn't change. So our inverse function is y equals the inverse sine of x. That means its domain will be the range of the old one, so -1 to 1. And the range is in -pi on 2 to pi on 2. This explains why, when you're using your calculator, it'll only give answers in between -pi on 2 and pi on 2, or if you're in degrees, -90 to 90. Okay? Remember that problem with the sine rule where it might be an obtuse angle and the calculator won't give you an obtuse angle? This is why, because the calculator is actually using the inverse sine function, and the inverse sine function doesn't give obtuse angles out as an answer. It only gives answers from -pi on 2 to pi on 2. Well, let's have a look at the curve. We would reflect it in y equals x. Now, it's a bit hard to reflect it here because of my scale. Remember, pi over there is 3.14, etc., etc. So pi would be a fair way up. So I'm just going to draw it on a separate one here. There we go. So it goes from -1 to 1, we know the domain, and -pi on 2 to pi on 2, the range. And basically, it's a piece of the sine curve, so we're drawing a sine curve in there. So it is not a cubic that you are drawing. It is not a tan curve that you're drawing. Right? It's the sine curve on its side. So if you do have one of those math aids, nice and easy. You just get your template, turn it sideways, and you can get the curve nicely. Let's have a look at the inverse cos then. What have we got to do with that one? So our original one, there's our original, y equals cos x. Can't use the same restriction. Okay, so domain all real x is not going to work. Fails the horizontal line test. I want to get all of the range in. But if I chose -pi on 2 to pi on 2, not going to work, because it would fail for this one. So I've got to choose a different restriction. And again, I'd like to include 0. So I guess I've got a choice there. I could go 0 to pi, or I could go 0 to -pi. And we tend to go with the positives rather than the negatives. So we'll go 0 to pi, and that'll get the complete range in there. So our inverse cos function, domain -1 to 1, the range is 0 to pi. That's why when you're using a calculator, cosine will give obtuse angles as an answer, because it's using the inverse cos function. Now, right, so your calculator is just using the function. What would our reflection look like for this one then? So again, let's plot it in. It's a piece of the cos curve, but now winding along the y-axis instead of the x-axis. Inverse tan then, what happens there? So our tan graph, there we go, whole heap of those little pieces and asymptotes. Again, fails the horizontal. Pretty easy to pick our restriction on this one, because I can get just one complete branch of that tan curve by just going between two of the asymptotes. And if I want to include 0, then the two asymptotes that I'll pick would be pi on 2 and -pi on 2. So my restricted domain, remember with the tan curve though, it's not equal to pi on 2 because they're asymptotes. So we're going between pi on 2 minus pi on 2. So inverse tan, other way around, domain will be all real x, But the range will be in between minus pi and 2 and pi and 2. So what will it look like when we do our reflection? Let's draw in minus pi and 2. There we go. It's a piece of the tan curve, but now the tan curve's on its side. So y equals inverse tan x. Okay, some properties when manipulating our inverse trig. Inverse sine of minus x is equal to minus the inverse sine of x. Now have a look at the picture we just drew for inverse sine. What do you notice about it? Anything? Other than it looks nice, it's quite odd. Very good. Yes, it's got rotational symmetry, you'll notice, about the origin. So it is an odd function. So function negative x is equal to negative function x. So inverse sine of negative. Cosine, if you look at that curve, it doesn't have any symmetry about the origin, but it does around pi on 2. So you get this interesting relationship. It's not that the inverse cos of minus x is equal to minus the inverse cos of x. Because you've shifted the curve up pi on 2, it actually becomes pi minus the inverse cos of x. Because there's a shift for both functions. So odd function that's been shifted up pi on 2. If you look at the inverse tan one, that does have rotational symmetry. So again, that's an odd function. Inverse tan of minus x is minus the inverse tan of x. And I guess the fourth one, inverse sine of x plus the inverse cos of x will always be pi on 2. Because if you think of a right angled triangle, other than the right angle itself, one angle would be the inverse sine of x, the other angle would be the inverse cos of x, if you draw the triangle. Remember, inverse sine, inverse cos, inverse tan, we're actually talking about an angle. They are angles. So we want to find the exact value of the inverse tan of root 3 minus the inverse tan of 1. Playing with exact values here, but we're talking about an angle. What angle has the exact value of root 3? Well, when we're talking about tan, of course. Anyway? Pi on 3 minus inverse tan of 1 pi on 4. Notice we're using radians. It's not degrees. If you say, what is the inverse tan of root 3 minus inverse tan of 1, it would be incorrect to say it is 60 minus 45. Because it's a value that we're coming up with, and that value is pi on 12, which is 3.14, etc., 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 divided by 12. It's not 60 minus 45, which is 15. Okay. Obviously, you get different answers. Well, the correct answer is when we're using radians. Inverse sine of 1 on root 2 minus the inverse sine of minus a half. All right, we could do minus a half, or we could use our rule up here and say inverse sine of minus half is minus the inverse sine of a half. I've just done it straight away, but you've got to be careful, because you've got to think about the range. Inverse sine will only give answers between minus pi on 2 and pi on 2. So the answer for minus a half has to be minus pi on 6. It's not 5 pi on 6. Oh no, minus. Oh, definitely not 5 pi on 6, because that would be positive. It's not, say, 7 pi on 6, the third quadrant answer. Because inverse sine can only give answers out in between minus pi on 2 and positive pi on 2. So minus pi on 6, 5 pi on 12. The cos of the inverse sine of 40 on 41, not one of our exact values. Remember, inverse sine, inverse cos, inverse tan, we're talking about an angle. So we're saying, what is the cosine of this particular angle? So we should come up with a ratio. So what I'm going to do, I'm just going to draw myself a little triangle here. There's an angle whose inverse sine is 40 on 41. So therefore, if that angle is the inverse sine of 40 on 41, that means the opposite over the hypotenuse is 40 over 41. And then I can use Pythagoras, work out the third side. So now I'm saying, what is the cosine of that particular angle? Well, adjacent over hypotenuse, it's 9 on 41. So inverse trig, remember, it's an angle. It's an angle. What about if I did it the other way around? The inverse sine of the sine of 5 pi on 6. This time I'm expecting an angle as an answer. Immediate reaction to most people when they first see this question is say, oh, it's 5 pi on 6. Because inverses cancel each other out. And inverse sine and sine are inverses. However, the inverse sine function cannot give the answer 5 pi on 6. It can only give answers in between minus pi on 2 and pi on 2. So what would be the equivalent angle to 5 pi on 6? 5 pi on 6, which quadrant? Second. In the second quadrant, is sine positive or negative? Positive. Therefore, if it's going in between minus pi on 2 and pi on 2, the answer is either going to be a positive acute angle or a negative acute angle. Which one do I want? Got to be the positive acute angle. So the equivalent acute angle to 5 pi on 6 is pi on 6. So be careful with those ones. Okay? You can only give answers out in the correct range. The sine of 2 inverse cos 3/5. Remember, inverse cos 3/5, we're talking about an angle. So that's really saying sine of 2 theta. You might even make it easier for yourself and say, okay, I know inverse cos of 3/5 is an angle. I'm going to call it theta. So it's now sine 2 theta, and I'll just draw up a diagram. Well, theta, it's that angle, the inverse cos of 3/5. So the adjacent over the hypotenuse is 3/5. That means the other side is 4. Now I can just read off my triangle. Sine 2 theta is, of course, 2 sine theta cos theta. Go back to the triangle, substitute in 4/5 times 3/5 times 2, and we get our answer 24 and 25. The inverse cos of 2 cos pi on 3. So this time it's the other way round. It's inverse cos of 2 cos. Well, we don't have a formula for that sort of thing. However, fortunately, cos pi on 3 I know the exact value of. So it worked out nice. What is the cos of pi on 3, by the way? And 2 times? So we get inverse cos of 1, which is 0. The tan of the inverse sine of 2/3 plus the inverse cos of 1/4. Again, we're talking about 2 angles there. So it's tan alpha plus beta. Alpha plus beta. So I'm going to let alpha be the inverse sine of 2/3 and draw up a triangle for alpha. So opposite over hypotenuse. Adjacent is root 5. I'm going to let beta be the inverse cos of 1/4. And this time it's cosine, so adjacent over hypotenuse is 1/4. The other side is root 15. Tan alpha plus beta is, of course, tan plus tan on 1 minus tan tan. Let's substitute in our ratio from our triangle. Multiply top and bottom by root 5, tidy that up a bit. Eventually we get there. There it is, 2 plus 5 roots. I didn't bother rationalising the denominator on that one. What's up? 1b.